Beneath the glittering surface of the ocean, there is a world where sunlight never arrives, and the weight of the water above could crush steel like a soda can. Down there, in the cold and the dark, lies a scar on the planet so deep it holds the record as the deepest known point on Earth's oceans, according to data compiled by the National Oceanic and Atmospheric Administration. We call it the Mariana Trench. To many, it's just a name on a map, but to geologists, biologists, and deep-sea explorers, it's something else entirely. A doorway, a portal into the history of how our planet was shaped, into the lives of bizarre creatures that survive under pressures we can barely imagine, and into the story of how far human curiosity is willing to go. Have we truly uncovered the secrets hidden in this abyss? Or are we only scratching the surface? If you travel to the far western edge of the Pacific Ocean, past the island chains and deep into the open blue, you reach a stretch of seafloor that suddenly plunges into darkness. This is where the Mariana Trench begins, just east of the Mariana Islands, a volcanic arc under U.S. jurisdiction that traces the curve of a massive tectonic boundary. It's remote, it's quiet, and it lies in one of the least accessible regions of the planet. Estimates vary slightly, but at its deepest point, the Challenger Deep, the seafloor plunges to about 37 feet, 10,984 meters, roughly 6.8 miles, 10.9 kilometers below the surface. To put that into perspective, if you took Mount Everest, all 89 meters of it, and dropped it into this trench, the summit wouldn't even break the surface. It would still sit nearly 2 kilometers beneath the waves. That's how extreme this place is, one of the most unreachable locations on Earth. But what makes the trench so deep, and why here? The answer lies in the slow but relentless motion of Earth's crust. The Mariana Trench is essentially the visible scar of a geologic process that has been reshaping the planet for millions of years. It was carved by subduction, the moment when one tectonic plate is forced beneath another. In this region, the massive Pacific plate is being pushed under the smaller Philippine Sea plate. The heavier oceanic crust dives into the mantle, while the lighter plate stays above, creating an enormous downward-bending fold in the seafloor. And this isn't just a simple crack. Beneath the waves is a tangled system of deformation zones where the ocean floor is squeezed, warped, and fractured. As the Pacific plate descends, parts of it heat up and melt, fueling underwater volcanoes and triggering frequent earthquakes. Those volcanic forces, over long spans of time, built the Mariana Islands themselves, a chain of peaks rising from the deep as evidence of the fiery processes happening below. Another factor adds to the trench's staggering depth: the age of the oceanic crust. The Pacific plate in this region is over 150 million years old, making it colder, denser, and more likely to sink deeper into the mantle. That extra weight helps drag the plate downward, steepening the trench and exaggerating the height difference between the seafloor and the land above. All of this, the sinking crust, the volcanic arcs, the constant recycling of oceanic plates, forms part of Earth's global tectonic cycle, a system that keeps the planet's surface in perpetual motion. The Mariana Trench stands as one of the clearest windows into that cycle, a reminder of how dynamic our world truly is, even in places we never see. And yet, as dramatic as the geology may be, the environment inside this abyss is even more astonishing. As we descend into the trench, the rules of the surface world fall away. The environment here is nothing short of brutal. At the bottom of Challenger Deep, the pressure reaches around 186 bar, a force so immense it's often compared to the weight of a commercial jet pressing down on a single fingertip. Down here, even metals can buckle, and anything unprepared simply doesn't survive. The temperature hovers just above freezing, roughly 1 to 4 degrees Celsius. It's a cold that never lifts, a chill untouched by seasons or sunlight. And speaking of sunlight, there is none. Not a single ray makes it to these depths. The Mariana Trench exists in permanent night, a darkness so complete that even the most advanced cameras struggle to capture what lies ahead. But the deep sea isn't uniform. Scattered along the trench floor are hydrothermal vents, cracks, where seawater meets superheated rock beneath the crust. When that water shoots back out, temperatures can spike to hundreds of degrees Celsius in an instant. Imagine going from near ice to boiling conditions within a few feet. That's the kind of chaos life must endure here. This staggering contrast, freezing cold just steps away from scalding heat, forces any organism hoping to survive to evolve extraordinary adaptations. And remarkably, many have. Life in the trench doesn't just survive. It rewrites the rulebook of biology. Down here, organisms live under pressures that would crush surface-dwelling life instantly, so their bodies have evolved in extraordinary ways. Their cells, for example, are reinforced, membranes become sturdier, proteins are built differently, and special molecules known as piezolites act like microscopic stabilizers, keeping those proteins from collapsing under the immense weight of the water above. Enzymes that would normally fail at shallow depths remain flexible and functional, even under more than 1,000 atmospheres of pressure. And because sunlight never reaches these depths, none of these creatures can rely on photosynthesis. Instead, life here draws its energy from chemistry. Entire ecosystems grow around hydrothermal vents, those underwater geysers releasing hydrogen sulfide, methane, and other compounds from deep within Earth's crust. Chemosynthetic bacteria feed on these chemicals, transforming them into energy. They are the base of the food web, the invisible engine keeping this alien world alive. But the stars of this strange ecosystem are the animals that have adapted to these extremes. One of the most iconic is the giant tube worm, Riftia pachyptila, which can reach nearly 2.4 meters in length. These worms cluster around vent openings like tall, pale chimneys. They have no mouths, no digestive tracts, nothing that resembles the feeding organs most animals rely on. Instead, they house symbiotic bacteria inside their bodies, bacteria that convert hydrogen sulfide into nutrients, effectively feeding the worm from the inside out. Then, there's the deep-sea Mariana snailfish, recorded at depths beyond 8,000 meters. It looks fragile, almost jelly-like, with a soft, gelatinous body rich in lipids and specialized biological compounds that help stabilize its cells under crushing pressure. Rather than hunting aggressively, it waits patiently for organic debris, what scientists call marine snow, to drift down from above. Even small creatures become giants here. Amphipods, normally tiny crustaceans, can grow to over 5 centimeters in the trench. This phenomenon, known as deep-sea gigantism, is common in cold, dark environments where slow metabolisms and long lifespans allow animals to reach unusual sizes. And near the vents you'll find blind shrimp, tiny explorers evolved specifically for a world without light. These shrimp have lost their vision entirely, but in exchange, their ability to sense heat and chemical trails is incredibly sharp, allowing them to locate the energy-rich plumes that sustain them. Alongside them are pressure-loving bacteria that not only form the base of the food chain, but also power the chemosynthetic processes that keep the entire system alive. What makes all of this even more remarkable is how useful these organisms might be to us. The biochemical compounds produced by deep-sea bacteria show promise in medicine, potential new antibiotics, even anti-cancer agents. Meanwhile, the structural tricks these creatures use to withstand pressure inspire engineers developing next-generation materials, submersibles, and deep ocean technology. And beyond Earth, these ecosystems offer a glimpse of what life might look like elsewhere. Worlds like Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, are believed to host oceans sealed beneath ice crusts, warmed not by sunlight, but by geothermal energy. If life can thrive in the pitch-black depths of the Mariana Trench, then perhaps it could thrive there too. But before we imagine alien oceans, we still have one more frontier to understand: humanity's own attempts to reach this forbidding place. Humanity's fascination with the deep began long before we had the tools to reach it. In the 19th century, scientists could only guess how far the ocean descended. Much of the seafloor was a blank space on maps, mysterious, unreachable, imagined more than understood. That began to change in 1875, when the British vessel HMS Challenger set out on one of the first global oceanographic expeditions. Using weighted lines and early sounding equipment, the crew recorded a depth of over 8,000 meters in what would later be known as the Mariana Trench. The measurement was groundbreaking, but the tools of the era were crude. The true depth remained uncertain, waiting for more precise instruments. It wasn't until 1951, when HMS Challenger 2 returned to the region, that clarity finally came. Armed with more advanced sonar technology, the crew confirmed the deepest point of the trench, Challenger Deep, and established it as the lowest known place on Earth's surface. From that moment, the trench wasn't just a geographic curiosity, it became a scientific target, drawing interest from researchers and explorers around the world. Then came the moment that changed everything. January 23, 1960. Swiss oceanographer Jacques Piccard and U.S. Navy Lieutenant Don Walsh climbed into a steel and plexiglass bathyscaphe called Trieste and began a descent no human had ever attempted. The submersible creaked and groaned as it dropped through the water column, its pressure sphere built to withstand forces equal to thousands of tons. After more than 5 hours, Trieste touched down on the seafloor of Challenger Deep. Against all odds, Piccard and Walsh had reached the bottom. They even reported seeing a flatfish-like creature swimming nearby, an observation later debated, since the environment seemed far too extreme for such a fish. But controversy aside, their dive marked the dawn of a new era in deep-sea exploration. More than half a century passed before another human attempted the journey alone. In 2012, filmmaker and explorer James Cameron piloted the deep-sea Challenger submersible on a solo dive to Challenger Deep. The bright green, vertically oriented craft carried him to the bottom, where he spent over 3 hours filming, collecting samples, and surveying the alien landscape. Equipped with cutting-edge cameras, Cameron returned with the first high-quality footage ever taken at those depths. He later described the seafloor as a moon-like desert, rugged, silent, and hauntingly empty. But every mission to the trench, whether crewed or robotic, comes at a steep cost. The pressure at Challenger Deep exceeds 1,000 times the atmospheric pressure at sea level. Under those conditions, almost any conventional material would collapse instantly. That's why submersibles like Deep Sea Challenger and the Triton 36,000 Anton 2 are built from titanium and specialized alloys, engineered to survive the unimaginable. Robotic explorers such as Nereus and Kaiko take on the riskiest tasks. These remotely operated or autonomous vehicles are outfitted with cameras, sampling tools, and environmental sensors. They roam the trench's contours where humans cannot, but they too face danger. Nereus, for example, was lost during a 2014 mission when the extreme pressure crushed its frame. Navigation poses its own problems. GPS doesn't work underwater, let alone 11 kilometers down, so expeditions rely on acoustic positioning systems to track their vehicles. And every dive requires massive funding. Each mission demands millions of dollars for equipment, crew, and logistics. Even then, submersibles can stay at depth for only limited periods due to energy constraints and the physical strain on both machines and people. All of this means one thing. Even with modern technology, exploring the Mariana Trench is still one of the most challenging endeavors on Earth. Even with decades of exploration, the Mariana Trench refuses to give up all its secrets. In fact, the deeper we look, the more questions seem to emerge. Over the years, a number of strange observations have fueled curiosity and sometimes wild speculation. Some expeditions have reported brief flashes of light deep near the trench floor. These weren't produced by submersible equipment, and they didn't match known camera artifacts. Scientists have suggested a few possibilities. Maybe they were chemical reactions triggered under extreme pressure, or perhaps the glow of bioluminescent organisms that haven't been identified yet. But without concrete evidence, the observations remain open-ended, inviting debate and, of course, imagination. Then there's the sound. In 2014, researchers documented an unusual acoustic signal in the region, a descending, then rising call lasting about 2.5 to 3.5 seconds. They named it the Western Pacific Bio Twang. Its frequency patterns didn't match any known marine species. Until 2016, some proposed it might come from a type of minke whale, such as the beaked whale, which is known for unconventional calls. But the match wasn't perfect. To this day, the origin of the bio twang remains unresolved, and whenever mysteries appear, legends follow. The Mariana Trench has become the backdrop for countless stories, tales of colossal sea creatures lurking below the reach of modern science, and rumors that the long-extinct megalodon, the gigantic prehistoric shark, might still roam the abyss. These ideas usually stem from blurry photos, vague anecdotes, or misinterpretations from deep-sea sonar. No verified scientific evidence supports them, but they endure because the unknown always leaves room for myth. But behind the folklore lies the trench's real importance, its scientific value, which is far greater than any urban legend. For scientists, the Mariana Trench is far more than a geographical extreme. It's a natural laboratory, one of the best on Earth for studying how our planet works beneath the surface. Here, the process of subduction plays out in real time. One tectonic plate dives beneath another, generating immense forces that trigger earthquakes, fuel underwater volcanoes, and constantly reshape the seafloor. By examining these interactions, researchers gain insight into seismic hazards, knowledge that's crucial for nations along the Pacific Ring of Fire, where millions of people live in zones vulnerable to quakes and tsunamis. But the trench doesn't just teach us about Earth. It serves as a window into the possibility of life elsewhere. The bacteria that thrive at extreme pressures and feed on chemical reactions without a single photon of sunlight offer a powerful clue. If organisms can survive here in perpetual darkness and crushing density, then similar life might exist in places like Europa or Enceladus, moons believed to harbor subsurface oceans warmed by geothermal activity. In many ways, the trench's hydrothermal ecosystems act as a preview of what extraterrestrial life could look like. There's also enormous biological potential hidden in these waters. Enzymes and other compounds produced by deep-sea microbes show remarkable resilience. Some have already drawn interest for pharmaceutical development, from potential antibiotics to molecules that might function in cancer treatments. Others could inspire new industrial processes, helping us create materials or machines capable of operating under extreme pressure, just as these organisms do every day. And then there's climate. The Mariana Trench plays a quiet but meaningful role in Earth's global carbon cycle. Organic particles from the upper ocean drift downward and eventually become buried in the trench's sediments, sometimes for millions of years. This process effectively locks away carbon, helping reduce the amount circulating in the atmosphere and slowing the pace of climate change. Scientists studying these deep carbon sinks believe that understanding how carbon becomes trapped at such depths could inform future strategies for greenhouse gas reduction. In other words, this one stretch of ocean floor influences geology, astrobiology, medicine, engineering, and even climate policy. But as vital as these insights are, they lead to an unsettling reality. Even the deepest, most isolated place on Earth is no longer untouched by human activity. Even a place as remote and unforgiving as the Mariana Trench hasn't escaped our footprint. In recent years, scientists collecting samples from Challenger Deep uncovered something unsettling: traces of microplastics, tiny fragments less than 5 millimeters across, embedded in the water and even inside deep-sea organisms. These particles didn't originate down here. They began life at the surface, where plastics break apart under sunlight and waves, and then drift downward through ocean currents before finally settling into the deepest place on Earth. And plastics aren't the only stowaways. Researchers have also detected persistent organic pollutants, industrial chemicals such as PCBs and PBDEs, in creatures living in the trench. Many of these substances were banned decades ago because of their toxicity, yet they remain in the environment for generations. Their presence in these animals is a stark reminder. Not even the abyss, once thought immune to human influence, is truly isolated. For the organisms here, the impact is profound. Life in the Mariana Trench already operates at the edge of what biology can endure: crushing pressure, scarce food, and intense cold. Adding toxic pollutants to that mix is a heavy burden. Amphipods have been found with microplastics and PCBs inside their bodies, meaning these contaminants can travel up the food chain. Even worse, the accumulation of plastics and chemicals can alter the physical and chemical properties of the seafloor environment, disrupting an ecosystem finely tuned to survive extreme conditions. Despite its depth, despite its isolation, the trench reflects a larger truth about our planet. No ecosystem is too distant to be affected by human actions. The Mariana Trench stands as one of Earth's last great frontiers, a natural wonder shaped by violence and pressure, yet filled with beauty, mystery, and life in its strangest forms. It draws scientists, explorers, and anyone captivated by the unknown. And even now, after more than a century of expeditions, most of this vast chasm remains uncharted, untouched, and unsolved. As one of the planet's last great unknowns, the trench is both a scientific treasure and a reminder of our responsibility to protect even the places we've never seen. So here's the question: what do you believe we'll discover next in the deepest part of our world? Drop your answer in the comments below. Thank you for watching and supporting the channel. Don't forget to subscribe so you won't miss the next deep sea exploration.